Okay, so let's continue. So we discussed Michelson-Morley experiment and the idea of light-carrying medium. Now we're going to talk about some peculiarity that Lorentz found, I guess by accident. Now Lorentz, so this is probably late 19th century, found that Maxwell's equations can be made invariant, but with a different type of transformation. If the following: x equals this funny factor times x prime plus dt prime. You'll notice the prime on the time, that's interesting. And time equals this factor squared times v over c squared times x prime plus t prime. So these are weird for several reasons. First, like, what are these factors? Second, notice the speed of light is inside these transformations. But the most peculiar one is that you transform not just space, but also time. Okay, so you have frame S that has its own coordinates and its own time, and a frame S prime that's moving with speed v that has its coordinates, but it also has its own time. Now, this was really just crazy. A time was assumed to be just sort of uniform everywhere for all observers, universal clock taking through the universe. And Lorentz had no idea. Okay, so these are called Lorentz transformations. He had no idea what's the mechanism for causing these transformations. He just found a peculiarity of Maxwell's equations, probably doodled around with math a lot, and he realized, oh, I can make them invariant under these transformations. He had no idea what they mean or where they're coming from. Well, he probably had some theories. So anyway, the point is, Lorentz found this peculiarity, and people tried to explain it in some weird mechanical terms so that the nil result in Michelson-Morley experiment would be justified, or would be explained. Okay. But by the way, what this implies is that this would preserve the form of Maxwell's equations, but now Newton's second law is not invariant anymore. So people weren't too happy about it. So that's Lorentz transformation. One other feature of electromagnetism that has to be mentioned, and it can be demonstrated with this magnet through the loop experiment. Okay, so I will talk about that now, and that might be it for today. And then we'll basically start with Einstein's postulates tomorrow. So electromagnetic theory, Maxwell's equations, has a peculiar symmetry built into it. And it's best to demonstrate it on the following. So let's say there's a loop of wire. Right, so here's magnet through the loop experiment. So imagine there's a loop and it's sitting on a cart, and that loop will pass through the magnet. That's what I was trying to draw here, okay? So this is from, the figure is taken from Introduction to Electrodynamics by Griffiths. So let's analyze this experiment. Let me go back to my doodles. So tell me, what's gonna happen? The car passes through the magnet, what will happen? Think about it. A current will be set up on the wire. And now what are the explanations for that? And the explanations seem to be completely different depending on which frame you're analyzing this experiment from. So explanations depend on the frame of reference. Okay, so current runs in the wire. And it's very easy to test in the lab. I'm sure they've shown you something like that in Physics 133 or this 3. So cars, I'm not sure why this is looking bad today. So how do you explain this from car's frame? From the car's perspective, what they see is they see a magnet approaching them. So when the magnet is far away, they see very low magnetic field. Then the magnetic field is increasing strongest, and then decreasing, weakest, okay? So the magnetic field is varying in strength as time goes on. And according to Faraday's law of induction, a changing magnetic field produces an induced electric field. And it is this induced electric field, and therefore electric force, that pushes electrons around the loop. Now, I understand that a lot of students who took Phys 3 don't realize that this is really what induction is about. Changing magnetic fields creates electric fields out of the vacuum. The way that students think about it, and this is incorrect, is that changing flux produces induced currents. Well, what if there are no wires around? Okay, so what is the current gonna flow in? Changing fields, changing magnetic field produces induced electric field, which then pushes the charges around, and that is the induced current, okay? So you're probably familiar with this, is that there is an induced EMF, which is basically like a voltage with the magnitude that's equal to d phi dt, or phi is magnetic flux through the wire. Magnetic field is changing, magnetic flux is changing, so d phi dt is non-zero, so there's an induced EMF, meaning meaning charges are pushed through the loop. You can use Ohm's law, V equals IR, or EMF equals IR. So EMF divided by the R is the current. Anyway, so that's the explanation from the perspective of people on the car, or from the perspective of the loop itself. How about from the ground's perspective? So this is from car's frame. Magnetic field is not changing. The magnet is sitting still. There is no temporal change of magnetic field. So if magnetic field is not changing in time, there is no induced electric field. So induction cannot be an explanation. But what they conclude is that electrons are moving in a magnetic field. Electrons that are sitting inside the loop. Remember, the loop is a bucket full of electrons. Circular bucket. And when you pass that bucket through magnetic field, there's going to be a magnetic force. What's that force? Force on moving charges. F equals Q V cross B. It's that pesky cross product that's giving everyone a headache. And it is this magnetic force is what drives the current through the wire. So you see if the velocity is in this direction and magnetic field is in this direction, V cross B is up, and that force is up. Well, if Q is negative, then the force will be down. In any case, so this is part of the loop, and so you push charges through the loop. This effect is called motional EMF. What's the EMF? So in other words, this idea still applies. And here, the flux is changing not because B is changing, not because B depends on time, but because more of the area of the loop is immersed in the stronger field as the loop passes through the magnet, and then less of the area of the loop is immersed through the field. Okay, so remember that flux is really the integral of B dot dA. Well, if this gives you cold sweat, think of this as just a dot product of B times A. Okay, B is constant, but A, the area of the loop through which the magnetic field pierces, changes in time. Okay, and so that's why there is a d phi dt. So this is called the motional EMF. Okay, it is not electromagnetic induction. But look, the formula is still the same. The answer is still the same. The answers are identical. The effect only depends on the relative velocities, but the explanations seem completely different. And since it did not appear that Maxwell's equations obey POR, it was believed that they're only right in the frame of the ether. So one of these explanations must have been correct and the other wrong. In other words, if Maxwell's equations are only correct in one particular frame, then all those ideas about induction, etc., are only correct in that one frame. So one has to accept the fact that the answers are the same by mere coincidence. This is extremely discomforting because clearly the answer should only depend on the relative velocity, because when you pull a wire through the magnet, or when you pull a magnet through the wire, how can answers possibly be different? And it was at this stage, with all the massive hints and massive confusion, that Einstein entered the scene. And to him, the symmetry of electrodynamics that I just presented was not an accident. And moreover, he was not willing to give up the simplicity and elegance of the principle of relativity, that all laws of nature should take the same form in different inertial frames. Really, in all reference frames, we're focusing on inertial frames. And so he writes a passage. I will post that passage. I don't want to just read it out loud. It won't go through very well. But in words, he says that the symmetry of the results seem to suggest that electromagnetic phenomena do obey principle of relativity. And Maxwell's equations should too. Perhaps then, principle of relativity should not be synonymous with Galilean transformations. Maybe the Galilean transformations are just wrong. There must be a different transformation that leaves the form of Maxwell's equations invariant in all inertial frames. And there is not a preferred frame in which they take the simplest form. Therefore, the speed c comes out of these invariant Maxwell's equations cannot be referenced to some particular frame as well. Well, if they're not referenced to any particular frame, then what is the speed relative to? And so that I suppose. I don't know exactly his thought pattern. But logically, that leads to, that forces us to a radical idea that the speed of light c is not relative to ether, but relative to any observer. In other words, that speed of light is the same when viewed from any reference frame. So Einstein proposed, he said, let's start from scratch. Forget all this ether business. It only makes things more complicated. I'm not willing to give up principle of relativity, but that sort of means that I have to just simply postulate that speed of light is the same in all reference frames. And so he proposed to start with these two postulates. And from them, he basically put all the pieces of the puzzle together. He showed where the Lorentz transformations come from. He showed that they naturally arrive from these postulates. That forced him to fix mechanics, though. Newton's second law had to be fixed. And from there, the famous E equals mc squared formula came from. But more importantly, these postulates led to a really radical idea that space and time are not independent, that they're interrelated, and all the other really interesting features that eventually leads us to the notion of black holes and gravity having a geometric meaning and so on. So tomorrow we will start with Einstein's postulates, and we will look at relativity of simultaneity. Thank you. Bye-bye.